So this will be one of the bonus tutorials in which I'm going to talk about the constraints. So most of you probably know already what parenting is. So if I grab a cube and I grab a sphere, if I make sure that the cube is part of the sphere, grab the UI. So I select the cube, select the sphere and hit P, which makes sure that it's parented. Now the cube becomes like the child, which scales, rotates and translates with the sphere. But I can still move the cube, scale it and rotate it wherever I want, and the sphere doesn't influence it any other than giving it its own scale and translations to it. So now let's back it off a bit. So I make sure that the cube is not a part of the sphere anymore. They're both two objects. And I'm going to talk about constraints. First one I want to go and talk about is the parent constraint. When you open the options, you can see that you have a couple of checkboxes in here. Most of the time you want to stay clear from the translate all and XYZ, all these kind of options, but you want to make the maintain offset work. So in this case I'm going to make the cube a little bit bigger, and what you have to keep in mind when doing constraints, when you do a parent you select the child and then the parent and do a parent selection and then it becomes the child of the parent. The constraints work in reverse. So first you select the one that's going to drive and then the driven one. And then when you hit constraint, and you will see here, if I don't check the maintain offset, it will pop into it. Now there's a connection you can see, there's a parent constraint. You can also see it when you select the cube, the channels become blue. What it's going to do is, whatever I'm going to do with sphere, which is the driver, if I'm going to rotate it, or if I'm going to move it, the cube is going to follow it. I can still do something with the cube. I can place it and I can rotate it. But now when I move or rotate the sphere, the cube is snapping back to the position that we already gave it, which is a different result than we had the sphere and the cube parented. So I'm going to do the parent thing here. So when I move this and I move the sphere, they keep the same distance. While when I move the cube here and I move this, it snaps back into place. So that's something we can use the parent constraints for. But also, if I want to, I'll just get rid of this cube, don't want it. We know that this cube is now in relationship to this sphere, but this sphere can take it over. So I select this sphere, I select this one, and then I set maintain offset on. So this distance and this rotation that it has, according to the sphere, will be kept there. So now this one can move whatever it wants, but its child is not listening because the parent constraint is taking over. I can now move this wherever I want, and wherever I do with the other ones, this one will always follow the sphere that is the one that has constraint. And as you can see, it nicely keeps the rotation and pacing that we have. But a parent constraint is not the only one that we have. Or first I'll explain a little bit why the selection is first the driver and then the driven. This is because you can have multiple objects have a driving influence on the last selection. So if I take the two spheres, I select the cube and then I select the parent with the offset on, nothing's changed. But now when I move this one, this sphere has like half of the influence on this cube, and this one is the same. So both have now a driving influence on the cube. Even with rotation, they can both drive this cube. What has happened is when you select the cube, you have the parent constraint as an input in there, and you can see the weights. So the p-sphere 2 has 1 weight and p-sphere 1 has 1 weight. If I would remove the weight from one of the spheres, now this one becomes the sole driver and this one doesn't do anything. I can switch this and you will see when I switch it, the cube already wants to go to the place where it was initially assigned to that sphere. So you can have as many possible objects driving just a single one, and then you use the weight of that constraint to switch in between. Now onto something different, and then is the point constraint. So we select the object or the driver, then the driven. We do a point constraint. Let's make sure that the maintain offset's off. As you can see, let's change the size a bit. It has the exact same position as a sphere. So if I move the sphere, the cube follows. But if I rotate the sphere, the cube doesn't follow. So I can now rotate the cube wherever I want. So as you can see, the sphere is staying in the same position. And if I move the sphere now, it keeps that rotation. So this is a nice way to take an object along while it can receive another rotation than it needs. And also this one we can do with an offset. So we select the sphere, select the cube, and we add the offset. What happens now is the cube has this offset relation because of the constraint. And if I rotate it, nothing happens. It stays in that exact spot. So this one will have always the exact same position as it is initially. And the same thing happens when you do an orient constraint. Let's remove the maintain offset. So whatever I do, rotation is taken into account, but movement is not. And if I do it with an offset, which means I can rotate this wherever I want, select the driver, select the driven, select the orient with maintain offset, and it will calculate the rotation offset that it already has, and then just calculate the rest of the rotations from there. And most people would think, but a parent constraint is like the same as a point and orient constraint. And I can show you that this is not the case. So first we do the parent constraint with offset, and let's do the point constraint with offset and the orient constraint with offset. Now if I rotate this, the offset is calculated, or the rotation is calculated within the offset, just like normal parenting does. Let's show that as well. So remove the empty node. So these two behave in a similar way, but if I select the last one with it, you can see it keeps the offset without the rotation from the point I'm rotating on. So in this case, the parent constraint behaves more like a parent-child relationship, while the point and orient constraint behave different. The point and orient constraint with an offset most of the time isn't used, but it is used without the offset a lot. Because if we do the parent constraint without offset on this one, and we do the point constraint on this one, and the orient constraint on this one, you can see that they behave exactly the same. But still, we do want to use the one with the point and orient constraint for these kind of relationships instead of the parent constraint. That is because when I rotate this one, it will only calculate the node with the rotation, so it will only calculate the orient constraint. And if I do the translation, it will only calculate the point constraint. With this one, if I do the translation, it will go through the parent constraint and it will calculate the orientations with the translations. So this is a little bit more heavy in calculations than with this one. Although with these tiny objects, not very noticeable, but if you have like a huge scene with a lot of these parent constraints, then it might be noticeable that there's a big difference in frame rate on the Maya viewport if you just use the point on orient constraint. It will save a little bit of time. So now we had the point, orient, and parent. Scale is similar, but it's separate from these three because these will only work with point or with translates and orients. Scale just copies the scale, and with an offset it will add that offset to the scale. And another one that we could use, let's keep a sphere and a cube, let's unparent them, let's delete the rest. And I created something that looks like this local rotation axis of the world here. So we're going to use an aim constraint. And an aim constraint in this case, I'll just show it first, is we can make one of these axes aim towards an object that we call the driver, and we can have an up object. So in this case, we want to have PQ4 as the up object. I'll just copy the name, because when we go to the aim constraint options, we have the world up type, and the up type is like the secondary axis. And we can fill in this name. It's not important right now, so first let's look at the aim vector. So we have a red vector, a green vector, and a blue vector. The red vector is the x, the green vector is the y, and the blue vector is the z. In the aim vector we have the same options. We have x, y, and z. We can fill in the values for these, but most of the time it's just using a value of 0, of 1, or -1. And in this case the aim vector that we set up is the x in 1. So you have to figure out that the position, like the middle of your selection, that point, it shoots an arrow out in the direction of x, which is the red line in this case, and that's the one is like the full length it can get. So we want to use that vector, in this case x, to point towards the next object. So if I select this, I select the object I want to aim towards, and then the object that needs to be aimed, and I hit apply, you will see that the red arrow is now pointing towards the sphere. And what they did with the up vector is, I said to the blue vector, you need to look towards this object. The problem is, this object is as static as can be. So when I say you need to look towards, with the blue, you need to look towards the up object that we give, the blue one cannot like rotate this way, because x has like the first choice. So what it does is, x will always make sure that red is pointing towards it, and then we rotate the x in such a way that the blue kinda looks towards the object that we have selected as an up object. So we form a line between this point and between this point, and over this line we will rotate so we can accommodate for the up object that we have here. If I delete this now, and I select I want to have the driver, I want to have the driven, and instead of x pointing forward, I want to have the green one pointing forward, I just have to say that the y, the green one, is in 1. And instead of having z being the up axis, I want to have the x being the up axis. I hit apply, and you can see it just switched. Y is now pointing forward, x is pointing up. But as I said, you have the values of 0, you have the zeros of 1, but you also have 0 or a number of minus 1 that you can use. So let's change the y that we had now into minus y. And what that does is, instead of pointing towards the object, it points away of the object. So if I hit apply, y should point that way, while x points towards the object, up object. And as you can see, whatever I do now, the y is nicely pointing away from the object that it needs to look at. And this is a nice and easy way to make sure that everything that an object nicely aims towards the next one. And that is it for the extra lesson on constraints. We're also going to talk about the pole vector, but this one is really easy and comes only into play when we have IK handles, which is covered in the next bonus lesson.